Hello, and welcome to another IB Math Speedrun with me, Vince. So today we're going to be going through the final part of Chapter 4, which is Chapter 4.5, and that's all about real-world applications of derivatives in calculus. So let's jump right in. So the first real-world application we have is optimization, and this is very common. It's all about finding the maximum or minimum of some kind of thing, really. Anything that we can model using mathematical functions. There's not much to say about it. There's no theories or anything you need to know about it. It's just imagine applying calculus to word problems. So the only real way to understand it is to jump into some questions. So that's what we're going to do. So the first question is, a rectangular plot of land is bounded on one side by a wall. Determine the largest area that can be enclosed using the wall and 800 meters of fencing. Okay, so this is a pretty simple problem. What we want to remember is, if it's the first time you're doing one of these problems, you might want to draw an image of what this might look like, especially if it's some form of geometrical problem like this. So what we have is we have a wall on one side, and then we have some form of fencing here. And we need to assign some variables to calculate the area. So say, let's call this height x, like this distance here, x, and therefore the distance of this side of the fence is also x, and therefore this remaining section of fence must be 800 minus 2x. Since it's bounded on one side by the wall, we don't need to worry about that side, and so we can create a function to model this, to model the area. So if you notice, we can simply model the area by multiplying x by 800 minus 2x, and so this will give us the area of the rectangle. So in other words, 800x minus 2x squared. And if we get the maximum of this function, we can get the maximum area that this enclosure can enclose. So to get the maximum, let's find the derivative of this function. So dy over dx is equal to 800 minus 4x, and so we have the maximum area will be when x is equal to 800 over 4, or in other words 200. So if x is equal to 200, this will enclose the maximum area. So we just now need to find the maximum area. So the maximum area is, well, we can use this function again. So this will be equal to 200 times 800 minus 2 times 200, which is 400. And so the maximum area we can enclose will simply be 80,000 square meters. My computer's lagging a bit. Okay. Anyways, x times 800 minus 2x. Yeah, so this should be 80,000. That's a bit weird. The book is giving a different answer. Have we modeled this wrong? Because the book is saying we should only have half the area, but I don't see anything wrong with our calculations. That's weird. So I don't know. I think the book is wrong in this case. Yeah. Okay. So we can now move on to the next question. So the next question is in a church building, A stained glass window is to be constructed in the shape of a semicircle whose straight edge sits on top of a rectangle. The diameter of the semicircle is the same length as the horizontal sides of the rectangle. If the perimeter of the window is to be 12 meters, determine the radius of the semicircle and dimensions of the rectangle that will allow the maximum amount of light to be let through. Okay, so again, let's draw a diagram. And so this would look like we have a semicircle on top of a rectangle. The perimeter of the window is to be 12 meters. So, and the diameter is the same length as the horizontal sides of the rectangle. Okay, determine the radius of the semicircle and dimensions of the rectangle that will allow the maximum amount of light to be through. Maximum amount of light in this case just meaning the largest area of the window. So the perimeter of the total window is 12 meters. So we know the perimeter of at least this part of the semicircle, the curved section, will be equal to, let's actually make some variables. Let's call this x. So the semicircle should be equal to pi times x over 2, the circumference, half of the circumference. And the perimeter of the rectangle, well, we can calculate this because we have the perimeter of the window to be 12 meters in total. So we have 12 is equal to, well, both of these sides are equal to 12 minus x minus pi x over 2. All over 2. This would be the length of these sides of the rectangle. So now we know all of that. We need to maximize the amount of light being let through, and so we need to get the maximum of this function. So in order to get that, let's calculate the areas of both. So we have 12 minus x minus pi x over 2 all over 2 times x plus pi x over 2 squared. And so this should give us the area. So, and we want to find the maximum of this function. Let's just expand this so it looks a bit neater. So we have first 12 over 2, which is 6, minus x squared over 2, minus pi x squared over 4, plus pi, this is going to be pi x squared over 4. So it cancels out, very interesting. Okay, so in this case, because these two cancel out, wonder why that is, but okay. We are left with this function, and so we need to maximize this function. So if we get the derivative, dy over dx is equal to simply negative x. Sorry about that. I'm back. I just realized this calculates the area of the entire circle when we only want to really calculate the area of half of the circle, so we have to divide this by 2. So actually, the final formula that we should get is 6x plus minus x over 2 minus pi x over 8, pi x squared over 8. Whoops. So knowing this, if we get the derivative of this, we have 6 minus x minus pi over 4 x. And so when this derivative is 0, x will be equal to, well, 6 divided by, 6 times 4 divided by pi plus 1, pi plus 4. And so this will be not equal to 6, it will actually be equal to around 3.36 meters. Knowing that this is equal to 3.36 meters, we now also need to find the height of the rectangle, which is y. And so we know that this is actually equal to 6 to 24 over 4 plus 5. And if we plug this into this y equation, we have 2 minus that, minus pi, actually I'm just going to use 3.36 because it's simpler. So 2 minus 3.36 minus pi times 3.36 over 2, 12 minus this, all over 2. And so this will be equal to 12 minus that, minus pi times answer divided by 2, all divided by 2. So this will be equal to around 1.68. Actually, it's just equal to half of 3.36. So that is that. Okay, now we can move on to the next question. And the next question is about this. So we have an open rectangular box is to be made from a piece of cardboard which measures 24 cm by 45 cm. The box is made by cutting out congruent squares from the corners of the cardboard and then folding up the sides of the remaining cardboard. Determine the dimensions of the box with the largest volume and calculate this. Okay, so if we have our diagram of a box, we need to cut out some parts from the corners, some congruent squares. So what do we know about the dimensions of the box? Well, let's call this part we cut out x. And so the final box will look something like this. So it will have a height, which is this part. No, sorry, it will have a width of this part, which is 45 minus 2x. It will have, I guess, not another width, but a length of 24 minus 2x. And it will have a height of simply x. And so we now need to optimize the volume. So we calculate what x is, or what the volume is, we get 45 minus 2x times 24 minus 2x times x. Yeah. And so we get, what is this, 45 Oops. Yeah. So we should get 45 times 24 times x. So this would be 10,080x minus 2 times 24 plus 2 times 45, which is 138x squared. And then we have plus, it appears to be plus 4x. Plus 4x cubed. So if we want to optimize this, well, we want to get the derivative. And so this is equal to 10,080 minus 138 times 2, 276x plus 12x squared. And so we need to find when this is equal to 0, so we'll plug it into the quadratic formula. So this is going to be 276 plus or minus the square root of 276 squared minus 4 times 1080 times 12 all over 1080 times 2, which is 2160. So we have 276 squared minus 4 times 1080 times 12. And if we square root that, we actually get 156. So we have 276 plus or minus the square root of 156 all over 2160. Oh, not the square root of 156, just 156. So it's clear that, actually it's not that clear. Let's get both values of what this could be. So one value is 156 plus 276 divided by 2160 is 19.93. And another value is 156 minus 276 minus 156 over 2160, which is equal to 0.05. Yeah. Yeah, okay. So now we have these two values. You actually need to figure out which one actually is a minimum and which one is a maximum. So I guess we can do that by getting the second derivative, which is d squared y over dx squared is equal to minus 276 plus 24x. And remember that if we have a positive value, it's a minimum, and if we have a negative value, it's a maximum. In this case, it looks like 0.05. Yeah. Oops, sorry, I just noticed a small mistake I've made. I put it over 2160, but actually the a value in this quadratic equation is only 12, so this should only be over 24. So the two possible values, x values we get are, we divide it by 24 and not 2160. Then we should get 276 plus 156 divided by 24. So we get the values 18, or 276 minus 156 over 24, which is 120, so 5. So we have 18 and 5. Okay, and so now we need to find which one is the maximum and which one is the minimum. And if we get the second derivative, as earlier, and we plug both of these numbers in, we should get that if we put 18 in, this will be obviously greater than 276, since we just divided it by 24 earlier. And so 5 will be the maximum value. So this box will have a maximum volume when this side is 5. So let's calculate the dimensions. 5, and then we have 24 minus 2 times 5, which is 14. And then we have 45 minus 2 times 5, which is 35. So we have 5 times 14 times 35, which is equal to 2450. So that should be, so this should be your maximum volume for this box. Okay, on to the next problem. And so that is, we have a cylindrical, a cylindrical can with, is to be designed to hold 1 liter of car engine oil. Find the surface area of the can that would allow the costs of material to be minimized. Okay, so in order for costs to be minimized, we actually have to find the minimum surface area, because the surface area is what will determine the costing of the material. If it has to hold 1 liter of car engine oil, 1 liter is equal to, it's not a meter cubed, it's I think it's equal to 10 centimeters cubed. It's equal to 1,000 cubic centimeters. Okay, so we can work with that. So we need to find, the volume has to be this, and we know the volume of a cylinder should be pi r squared h. So this must be equal to 1,000 centimeters cubed. So what can we get from this? I guess we can get h must be equal to 1,000 over pi r squared. And so we now need to find the surface area of the cylinder. And so the surface area of a cylinder is equal to 2 pi r h plus 2 pi r squared, because 2 pi r h is the rectangular surface that goes around, and then we need to add the top and bottom circles. And so we substitute 100 over pi r squared into here, then we will get 500 over r times h plus 2 pi r. Oh, so not times h anymore, this is already h. So it's 500 over r times 2 pi r squared, and we need to, minimize? We need to minimize this function. So you can do that by squaring this, so it's 500. Actually, let's not square it, that's a bad idea. So let's get the derivative, dy over dx. So this will be equal to negative 500 r to the negative 2 plus 4 pi r. So we need to find the values for which this is equal to 0. So 0 is equal to negative 500 r to the negative 2 plus 4 pi r. So if we multiply both sides by r squared, we get 4 pi r cubed minus 500 is equal to 0. And so r cubed is equal to 500 over 4 pi. So r must be equal to, well, 500 divided by 4 pi, and we need to cube root this. So what I'm getting is something like 3.41 centimeters for the radius. What? Hold on. Is this right? Pi r squared h, 100, h equals 1000 over pi r squared. Well, this makes sense, I guess. Let's just put it in to see what we get as the surface area, if it's something reasonable. So we know h is 1000 pi r squared. So therefore this must be 1000 divided by pi times, well, 3.41 squared. So this is equal to pi divided by answer squared. So this is equal to roughly 27.3 centimeters. So the surface area would be, well, actually we can use this formula, right? 500 over r times 2 pi r. So with r being 3.1, this is 500 over 3.41 plus 2 times pi times 3.41 squared. Oh, sorry, why are we dividing by 2? We should be multiplying by 2, actually. So this should be 2000. So we have 2000 over r, so now this makes it negative 2000 over r. I'm going to skip all of this. Just imagine it's 2000 in the place of 500. So we get r cubed is equal to 2000 over 4 pi, and that's equal to 159. So if we get the cube root of that, we get a more reasonable answer, which is 5.42. So if we plug 5.42 back into this original formula, we get 2 pi r h, 2000 over r plus 2 pi r squared. So this is 2000 over 5.42 plus 2 times pi times that answer squared, and we get something like 553.58. So yeah, a much more reasonable answer for the surface area, so that's what's correct. Okay, now on to number 9, and it is find the shortest distance between the 1.50 and the curve y is equal to the square root of x. So, well, how are we going to calculate the distance between these 2 points? Well, I guess we could express it in terms of x. So the value of the x difference will be the absolute value of 1.5 minus x, and the y difference will be the square root of x minus 0. So just the square root of x will be the distance in y. And to find the shortest distance, well, we need to find a function that expresses this distance, and we can use the Pythagorean theorem, 1.5 minus x squared plus square root x squared, which is x. So we would get x squared minus 3x, so it's actually only minus 2x, plus 2.25, all square root. So we need to find the maximum of this function here. Oh, sorry, not the maximum, the minimum of this function here. So we can use chain rule, I guess. So we have y is equal to this, say it's equal to 1/2 u, and u is equal to x squared minus 2x plus 2.25. So using chain rule, we get that dy over dx is equal to 2x minus 2 times x squared minus 2x plus 2.25. Sorry, actually 1/2 times all of this. So it's x minus 1 times x squared minus 2x plus 2.25 to the negative 1/2. So, knowing that, what do we get? This is x minus 1. Since this part over here cannot be 0, our only real root is, I think, x is equal to 1. So at this point, we need to find the distance. So we'll put it back into the original equation. When x equals 1, we have 1 minus 2 plus 2.25. Right? So we have 1 minus 2, negative 1 plus 2.25. We have the square root of 1.25. Is that it? I mean, this is the square root of 5 over 4. So this would be the square root of 5 over 2, I guess. Yeah, I guess this sort of makes sense. So yeah, this would be the answer. Okay, on to the final problem. And the final problem is that you are designing a poster to have a printed area of 320 centimeters squared. The margins are at the top and bottom of the poster are to be 5 centimeters each, and the side margins are to be 4 centimeters each. Find the dimensions of the poster with the smallest total area. So printed area of 320 centimeters squared, and the margins, the top and the bottom, are 5 centimeters each, and the side margins are 4 centimeters each. Find the dimensions of the poster with the smallest total area. Okay. So to get the total area, well, we know, let's call the x value, or the width of the printed area, x, and so the height of the printed area will be 320 over x. So to get the total width, we have to get x plus 5. That's top and bottom. Side margins are 4 centimeters each, so it's actually x plus 8. And to get the total height of the poster, it will be 320 over x plus 10, since 5 times 2. Okay, so if we multiply this out, we get 320 plus 8 times 320, which is 1,280 over x, plus 10x plus 80. So this would be equal to 400 plus 1,280 over x plus 10x. So we need to get the derivative of this, and the derivative will be dy over dx is equal to negative 1,280x to the negative 2 plus 10, and so we need to find when this is equal to 0. So 0 is equal to this, and so we can also say 0 is equal to negative 1,280 plus 10x squared. So we have x is equal to the square root of 128, which is 8 square root 2. So x equal to 8 square root 2, I believe. Hold up, am I making a mistake? 8 times 32. Oh, sorry, this is 256. What am I doing? Cannot do mental math today. Anyways, this is 2560. So this is 2560. This is negative 2560. And so we actually have x is equal to the square root of 2560 over 10, which is equal to the square root of 256, so 16. So the total width of the poster is actually 24, since we add 2. Since x is 16, the total height, which is 320 over 16, which is 20 plus 10, so the height should be 30. So the poster should be 24x30. So yeah, that was it for this speedrun. I hope you enjoyed it, and I hope to see you in the next one. See you then.